This is a fun one. So we got two asteroids of mass 2m and 6m, and they're a distance L apart. At some point between them, the force on a third mass would be 0. If the force on a third mass would be 0, what does that mean about the gravitational field? It is 0, right? The gravitational field at that point is 0. Where is that point going to be, roughly? Towards the right?
Like not in the middle, but right. Right up. No.
Which one's going to exert a greater gravitational force on a mass if you put it in the middle? 6m, because it's bigger. So in order for them to balance out, it's got to be over here somewhere. Okay. Gravitational field is going to be 0, which means the gravitational field from this guy must be equal to the gravitational field from this guy. We're trying to find the point where the force on a third mass would be 0, which is the point where the gravitational field is 0. Total gravitational field is 0. So the gravitational field from 6m would be to the right, and that would be g times 6m over what? Well, the question is how far from the asteroid of mass 2m is the thing, so I'll give make a variable for that distance. So then 6m, what would we plug in? L minus x, right. And that minus, then the gravitational force from 2m will be to the left, so we subtract g times 2m over x squared. And those have to add up to 0, which means those two are then equal. So that minus that equals 0, so those two things are equal to each other. Bye by m, bye by g, cross multiply. And you despair because you think it's quadratic, but you can cheat and square root both sides. Not really cheat. Actually, you could cancel these down to 1 and 3 first. That'll be nicer. So then over here we have root 3x equals L minus x. So what does that give us? X times root 3 plus 1 equals L. So x equals L over root 3 plus 1. And since we're physicists, I like to get decimals. So that's about 0.366 L. Which kind of makes sense because it's closer to 2m. You okay, Tan?
Wow. I was kind of confused. Why would it be more to the left? So,
which one will exert a stronger gravitational force?
Would it be the 6m?
Right.
So
in order for the gravitational force to be equal, you then have to be farther away from the 6m, closer to the 2m, or for the gravitational field to be equal.
Okay.
Yeah. Alrighty then. So density, you guys know what density is. What's density? Mass over volume. And we've done a lot of v equals velocity, so I'm going to write out the word volume. The density equals mass over volume is actually on the formula sheet, I believe. The only way that I have seen density show up on the AP exam is a question like number 14 here. The planet has a quarter of the density and 3 times the radius of Earth. Determine the gravitational acceleration at its surface. Okay. So it's questions like that show up in the multiple choice from time to time. So we know we're gravitational acceleration, we're dealing with g times m over r squared, right? But this adds another layer of complexity because we know something about the density, not about the mass directly of this other planet. So then we have to think, okay, well, density is mass over volume, so mass is density times volume. Density is the Greek letter rho, which looks like a P. Yeah, that's right, we did. And what is the volume of a planet? Yes. And surface area is the derivative of volume.
Really? Oh, is that why it's just
4 pi r squared.
Oh.
How about that? That may only work for spheres, though, because the surface is all an equal distance away from the origin of a three-dimensional coordinate system. So you can take a derivative with respect to r. I don't think that works for other shapes. Anyway, so that is the mass. So we can plug that in, acceleration to gravity, g times 4/3 pi r cubed rho over r squared. So what happens to our r's? Two factors of r go bye-bye. We've got a 4/3 g pi r rho. So we have that the gravitational acceleration is then, if we write it in terms of radius and density, is directly proportional to both, to the product of radius and density. So if we have quarter the density, 3 times the radius, that gives us a factor of 3/4 of the gravitational acceleration on the surface of Earth. Does that make sense? So you go 3r, you get 3 times the gravitational acceleration, quarter the density, gives you 1/4 the gravitational acceleration. Together that gives you a factor of 3/4. Okay. And this would probably be a multiple choice question, so it might be this or it might be the decimal equivalent, 3/4 times 9.8. So yeah, so know what density is and how to fiddle with that. That's it for content for today. There's this interesting, this is just a interesting historical note. This guy named Henry Cavendish designed an experiment to determine the value of G. It involved what's called a torsional pendulum, which is like a wire that twists. You know, if you twist a wire up, or like a swing set, if you twist it up, it'll twist and then stop, go back, or whatever. That's what a torsion pendulum is. It's a twisty thing. He designed an experiment involving a torsional pendulum. It's really very clever. Maybe I'll show it to you when we talk about torsion pendulums, because it won't make sense until then. And he got the value of G to be 6.75. 67, not too far off. And this was the first good measurement of G that we really had, and that's more than a century, more than 100 years after Newton published his law of gravitation. So Newton didn't say G equals 6 point something. Newton said it's something times m1, m2 over r squared. So using G, they then were able to calculate Earth's mass with a reasonable degree of accuracy, and this is how we first discovered that Earth was not of uniform density, because calculating the mass of Earth and knowing the volume of Earth, they were able to see that the average density of Earth was higher than the density of rocks near the surface of the Earth that we had, done experiments with. So that's what led them to the conclusion that there must be some sort of structure in how the Earth is formed. Now we think, the core, mantle, whatever. Like, it was because of density that they started thinking about what might be in the Earth instead of assuming it was the same all the way down, and that it is in fact denser close to the center of the Earth than it is at the surface. It's interesting. The Moon, however, the average density of the Moon is basically the same as the rocks on the surface of the Moon, so nobody has done anything to investigate what might be inside the Moon because it's probably all the same. But maybe there could be something inside the Moon that's interesting, but they decided it wasn't worth investigating. It's expensive to get stuff up there. But yeah, there doesn't seem to be anything different going on there. This is your homework. One other thing I want to mention, there was a question on the multiple choice segment of the exam once. It's really complicated to figure out, so I don't really know if it's worth learning it when it probably won't show up, and even if it does, it'll be like one question. But about a tunnel going to the center of the Earth, and I do want to talk about the concept, because if you're in a tunnel going to the center of the Earth, what's going to happen to the gravitational force as you get closer to the center of the Earth? So Newton's law of universal gravitation says gm1m2 over r squared, right? However, when you get to a point here, consider the mass, some of the mass is pulling you this way, but now there's mass over here on the other side of you that's going to pull you in the opposite direction. So the 1 over r squared dependency only works when if r is the radius of the Earth, then for radii bigger than r, then we have a force that is proportional to 1 over r squared. Okay? But when you get inside the surface, there is less mass pulling you inward and more mass pulling you outward. So as you go, the gravitational force on you was gradually decreasing. When you get to the center, if you were able to get to the center of the Earth, the gravitational force on you would be 0, because the mass is all around you, kind of pulling you outward. Okay? And it turns out that for radii inside the Earth, gravitational force is actually directly proportional to your distance. Again, this is for a uniform sphere, so Earth itself is a little more complicated than that. But for a uniform sphere, it's that because the mass, you can use law of gravitation, but you have to use, like if you're here, you have to use the mass enclosed in like this sphere right here, which, like we did with the density, the mass enclosed in this sphere is proportional to your radius cubed, and then the gravitational force is proportional, or inversely proportional to radius squared, so those cancel out, leaving you with a factor of r. Yeah. Anyway, it's a calculus thing to actually calculate it out. But interesting deal. So conceptually, you can now know if you have a uniform object, as you tunnel in, gravitational force will get smaller and smaller linearly as you go towards the center.